Alright, welcome to my part 2 where we actually implement the whole transformer. If you haven't seen my part 1 where I basically explain how the transformer works in general, I highly recommend it to check it out. But yeah, without further ado, we can actually start to code it. I prepared some of the function already, and obviously we start with torch. We also got the math module and torch functional to get the, I think, softmax. We create each class for each basically part of the network. So for embeddings, positional encodings, for attention mechanism, for feed-forward network, encoder layer, decoder layer, and encoder decoder structures. And then at the end we got the classifier and transformer. And after each of this class, I prepared also the test function, so it will be easier to pick up the bugs that we have in the code, and we can fix them so much faster. All right. Also, I did already init function, and we only need to add some information in the init and just add information in the forward function. By the way, let me know in the comments what you think about it. Do you want me to write these things from scratch or just keep it the way it is? Because I think like calling the super function and initialize all these variables from scratch and rewriting it doesn't make really sense, and we can do much more in a less time when we actually got predefined some of the code or pre-written some of the code and just get to the meat of the problem rather than just wasting time on writing them from scratch. So yeah, let me know in a comment. But yeah, so I predefined some of the parameters of the network which are described in a paper. So basically we got 8 heads. The embedding size is 512. We've got expansion size in the feed-forward module 2048. We got 6 layers and dropout rate is 0.1. So I also prepare our source sentence and target sentence. So source sentence gonna take from 0 to 100 a random integer, and the size of it is going to be 41. So basically each word has one index from the vocabulary. So technically our vocabulary is 100 words. Obviously it's just a toy example, so it doesn't really matter. But the target sentence has a sample from 0 to 49 integers to 50 integer and has shape 2. So basically we got 2 words and 4 words. So basically we got 2 words in a target sentence. Okay, okay, so that's basically the whole function. Now we can try and see if it works. So vocabulary size is going to be 100 for source sentence, right? So yeah, sorry, I changed it to 1, 4 and 1, 2. It's going to be just easier for the calculations. So yeah, as you can see, each word, 1 can denote the batch. So one example in the batch. But yeah, we got 4 words and each word has a 512 feature representation. So that's what we wanted. Now we can actually move to our positional encoding. So it takes 3 parameters. Basically, D is the embedding size again, P is the probability of dropout, and we got the max length. It basically denotes how much of this geometric progression we need to calculate for how many words. Okay, so to start with, we define the self PE, and we basically define it with zeros, max length, and D. Right, so this is where we're going to store our positions. So we also got the position of the word, which is, so this is going to be value from 0 to max length. And then, as you can see, the value that we divide the position, pretty much the same. It depends only on the embedding. So this is going to be 10,000 to the power, and then we need to arrange. So this is from 0 to D and 2, and we need to multiply it by 2 and divide it by D. Okay, and now we need to just calculate the self PE from, so every second value is going to be equal torch sinus from position divided by diff. And then every odd number if in PE, it's going to be cosinus position divided by 2. Okay, now we need to just define dropout from P, and yeah. X is going to be the output of the embedding, so basically we need to sum it, and obviously pass it through dropout. So it's going to be X plus PE, but obviously it has 100 positions, but our input doesn't have 100 positions, and can have, in our case, it's only 4. So we need to scale it. We basically only select 4 of the first positions in PE, so it's going to be X dot shape from 0, and yeah, from 1. Yeah, we got our output, but we need to unsqueeze the position, because then we can't apply it in self PE. Okay, so you need to unsqueeze it, and yeah, we obviously do it for each position, but every second embedding, right? And obviously here, I just forgot to add it. Okay, so that should be it, and it works. It returns our embedding size, that's what we wanted, and we add on the top of it the positional information. So now we get to the meat of the whole paper, so the self-attention. As you can see, we've got the 3 linear projections, and we're gonna query keys and values, but before we do it, we need to predefine the heads, because later on when we're gonna reshape them and create the multi-head attention, we need to have the dimension of the head dimension and all that stuff together. So that's why you need to predefine them. Okay, so we got self heads. We need to have head dim. So this is going to be D divided by heads, and self D is equal to G. All right, now we can define our query keys and values, and it's going to be linear from head. So it takes head features, in features as a head dim, and output it's also going to be a head dim, and we pretty much do the same for keys and values. Okay, so now what we need to do, we also need to define layer normalization, which is layer norm, and it's going to be D. So that's pretty much it. Now we can move to the forward function. We start with getting a batch from Q. So Q, that shape from 0, because obviously we need those values for reshaping the vectors later on. So we got batch value, we got query length. So this is going to be Q shape from 1, key length, and value length. Okay. Now what we actually do is we create query, key, and value. So query is going to be self Q from Q, but we need to reshape it. So we reshape it to batch, query length, heads, and head dimension. And we obviously do it the same for query and values. Okay. Okay, so now we got our query key and values, and now we calculate the dot product. We're actually going to use ANSUM function. So what it does, we actually got the dimension of batch, query length, heads, and head dimension. And the dimension of keys is batch, key length, head dimensions. And what we want to achieve is a batch, heads. So for each head, we got attention score between query and key. And we obviously going to do it between query and key. Okay, so then what we need to do is basically scale it. So we do it by, so we divided my math square from self D. And now we need to, if we have mask, we obviously need to apply mask. So if mask is not none, so then we apply the mask on the scale. So scale is masked fill. So if our mask is equal to 0, then we apply float minus infinity. And we apply minus infinity because when we apply later on softmax on it, it's gonna reduce it to 0. Okay, And that's what we want in our mask. We want to have 0 values. We pass our scale through softmax. F softmax. The input is scale and the dimension is 3, so we apply it on the key values. Then we got the attention score. So this is our attention score basically. And now we multiply it with the value. So again, we're going to use torch ainsum to do it. So this is going to be the softmax shape. It's going to be batch heads query key, and the values is batch values length, heads and head dimensions, and what we want batch query length, head and head dimensions. We perform it between softmax and values. Then we need to concatenate it, and we do it by reshaping the output. Reshape batch query length self d, and then we pass it through linear function that we need to define. So let's call it linear, and input gonna be self d and the output's gonna be self d. Okay. So it's gonna be add norm, which is equal to linear plus query, and we're gonna apply normalization on the top of it, and obviously return add norm. Yeah, let's see if it's actually gonna work. So we pass here heads and dimensions, as you can see, and our input to it is gonna be output of positional encodings and embeddings. So let's see if it works. All right, one thing that I fixed, it was heads dim rather than head dim, and yeah, it returns basically the input we gave, so it works. All right, now we can move to feed forward. It pretty much takes the same. It's got the embedding dimension and the expansion dimension. So it's gonna be we're gonna actually do it in a sequential module. So we got an linear, which takes D and outputs DFF. Then we got ReLU, then another NN linear on the top of it, which gonna takes DNF and returns D. Okay, so that's basically it. We need to also add the self norm, so layer normalization, and from D, and I guess that's pretty much it. And also we need to add dropout, and yeah, that's pretty much it. So what we do here is return self norm from X plus self FF from X, and yeah, it seems like that's only it. So as an input we pass the output from the self-attention mechanism, and then previously we passed it through. So obviously the input is going to be the output of self-attention. Okay, so this is let's see if it works. Yeah. All right, so now we can combine it into Encoder Layer, and it's going to be it obviously takes heads D and DFF. What it basically does, it's just we combine the feed-forward network and the multi-head attention from the encoder. So that's pretty much it. So we got our self-attention mechanism, so we call it self, and we pass here heads and D, and we got feed-forward, which is feed-forward. Again, it takes D and DFF. And then we just basically pass it in the forward function. So it's going to be return FF from self-attention from query keys and values. Obviously, this value is going to be the same in the encoder. They're going to change in decoder. Our X in this case is going to be the output of positional encoder and embeddings. So we pass our source sentence here, and we see what's going to be the output of it. There we go, that's what we wanted. Now we got the decoder layer. Decoder layer has 3 sub-layers. It has 2 multi-head attention mechanism and 1 fully connected feed-forward network on the top of it. All right, so to start with, we need to define our attention mechanism. Let's call it mask attention. Okay, attention, we obviously pass heads and D here. And as you can see, basically the top of the decoder it's the same as encoder layer. So we just call it enc layer, and it's gonna be encoder layer. We pass heads, D, and DFF. Okay. The output of masked attention is gonna be query. So it's gonna be self masked attention, and we pass here x x x. So this is our target sentence, and we also apply the target mask over there, right? So this is going to return the query, but in the encoder layer, so this is what we're going to return. We pass query key value, right? So this is the values from the encoder. Okay, yeah, that's it. We can't actually test it right now because we don't have a target mask defined yet, but we're going to do it in an encoder decoder structure. So encoder decoder structure basically combine so this is basically the whole structure without the positional encodings and the classification and embedding, so obviously. So obviously we have multiple of encoder layers and decoder layers defined by the number by the n number. Let's call it enc layers, and we're going to store them in the nn module list. Yeah, we just basically so it's going to be encoder layer heads D and DFF, and we are going to iterate. We're going to create n numbers of them. Then we have decoder layers, which is going to be again nn module, but we just basically create decoder layers. Okay, that should be pretty straightforward. Now we got the forward function, and so we start with getting our source sentence and passing. It's obviously source sentence after the positional encodings and embeddings, and we pass it through the encoders layers first for enc for each layer in encoder layer. We got the source. Obviously later on we pass this value as a value and keys in decoder. And then the output of the decoder is going to be dec, and we pass here target, source, and source, so there's going to be value and keys taken from the encoder. And obviously we need to pass the mask, and we're going to define the function to do it. Okay, so as you can see, we passed target here. So the target shape is 1, so the badge, the number of the words, which is 4, and the 512, right? Okay, so we extract the badge shape and the number of words in the target sentence, so tarclen, and it's going to be, okay. So we need to create the mask, so it's going to be torch trill. And let me show you what this function does. So as you remember, we want to zero out the future values, and we don't want to have contextualized information about the words that we want to predict. So we basically zero out the values above the diagonal. Okay, so as you can see here, this is the example. We got the random tensor, we applied torch trill, and we got this value. Okay, so that's what we actually going to replicate. So first of all, we need to create metrics with 1 values. So this is going to represent the words that are going to stay, and the rest is going to be 0. Okay, so now we have the mask, and we just basically reshape it. So mask, reshape. So we reshape it to for each example in a batch. Okay, so it's going to be target. And that's basically it. Yeah, we just need to return in the forward function our target. Let's see if it works. So our source and target is going to be first passed through the positional encoding and embeddings, and we'll see if it's actually... Okay, so there was like a huge mistake from my side. When we reshape here in self-attention, I leave the query here, so I got Q instead of K. So yeah, it couldn't reshape, and we got the error in a encoder decoder. I fixed it. Then the last thing, we've got the classifier on the top of the network, and this is straightforward. It's just basically a linear which takes D, So embedding size, the output feature is going to be target vocabulary size. Obviously return it. So we define our target vocabulary size. We pass the output of encoder decoder. So yeah, we've got two words with the probability distribution over 50 values. Obviously we didn't apply softmax, but it's going to be applied on a loss function, right? Okay, now we can combine it all together in the transformer class. So yeah, we've got our encoder decoder structure where we pass heads, the DFF and number of layers. We got our positional encoding, so it's PE with where we pass D and P. We also got the embeddings, so it's going to be source embeddings. Obviously they're going to be different than the target embeddings. Source embeddings going to be embedding, so D and source vocabulary size, and target embeddings will be embedding D and target vocab size. Okay, now basically the last thing we need is a classifier. So and D and target vocabulary size. And yeah, now the only thing left is forward function. We got the embeddings and positional information for our source sentence. We got pretty much the same for target. Then we just basically pass it through the encoder decoder and we got the output. So and we return the output of the classifier. So that's the whole transformer. Hopefully it's going to work. So let's set our source vocabulary size to 100 and target vocabulary size to 50. And yeah, there you go. We got, again, that's what we wanted, two outputs with the probability distribution of a target vocabulary size. Okay, so that was the second part of the transformer videos. If you enjoy it, please leave a like and hit the subscribe button. And yeah, hopefully see you in the next video. Cheers.